Welcome to Ashby Village Science and Ideas Group. My name is Joe Evinger. I help coordinate this group's events with Hillary, whom you've just heard speak to us. All of our members here at the Ashby Village Science Group have varied educational backgrounds and work experience, and we all share a common interest in science and new ideas. We currently have over 60 members in our group and another 60 on our guest list. We meet via Zoom the second Thursday of every month from 3 o'clock until about 4:30. We have a different guest speaker each month who speaks to us on a topic related to science and ideas. We rely on our science group members, the Arts and Cultural Committee, Ashby Village members, our invitees, presenters, and others for ideas about new speakers and ways to connect with them. Besides our presentation today, I am, of course, actively recruiting speakers who might speak to us in the coming months. Here are some upcoming topics. In January, we have a physicist, Professor Sean Gavin from Wayne State, who will explain how a collision, metaphorically, between Charles Darwin and Lord Kelvin kind of gave us the rise to modern cosmology. His presentation is entitled Delusion, Fusion, and the Age of the Sun. In February, Dr. John Schwartzberg will give us an update about COVID-19. In April, a geologist, Seth Finnegan, will speak to us. His presentation is titled Mass Extinctions and Ancient Climate Catastrophes. We invite all Ashby Village members to join our group, and also others interested in Ashby Village and our presentations. They are also always welcome. Today, though, we're going to hear a topic, the James Webb Space Telescope, a new look at the universe. Speaking to us today will be Larry Toy, retired astronomer, PhD. Larry received his degree from Harvard and his master's and PhD degrees from UC Berkeley, all in astronomy. Excuse me for a second. Larry will move on. He spent much of his career teaching astronomy at Chabot College. He was honored as one of the first 4 outstanding faculty selected from the 15,000 faculty of the California Community College. He is a founding board member of the Chabot and Space Science Center in the Oakland Hills. For the final decade of his career, Larry served as founding president and CEO of the Foundation for California Community College. Larry has served as president of Lamorinda Village for the past 3 years, and he tells me that those 3 years have recently ended. So now I present to you Larry Toy.
Thank you very much, Joe, and thank you for the kind introduction. I'd like to share with you some slides, and I'm going to move to my share screen if I get it correctly, and hopefully you will be able to see that. Can everyone see that? James
Yes.
Webb Space Telescope. You can nod yes and up,
yes.
Heads up and down. That'd be great. And we'll start. I have to tell you a little story. I came to Berkeley in 1967 for graduate school, and it was the summer of love. So that was quite an interesting time. And one of my most interesting experiences during that time was one of the graduate students, a woman named Diane Piper, was just finishing her degree. And we found out that we both loved opera. And she turned out her professor, who was at Berkeley, had transferred to the new Santa Cruz campus because all the astronomers who were based on at Lick Observatory, who used to be at Berkeley, were moved to form an instant department of astronomy at Santa Cruz. And so she became the first PhD to graduate from the University of California at Santa Cruz. But the big deal that she did was she had a extra ticket, which she couldn't go to the opera, San Francisco Opera, in September. So she said, "Would you like the ticket?" I said, "Oh, yes." And she said, "What's playing?" She said, "La Boheme." I said, "Oh, that's great. It's one of my favorite operas." So I went there, and there was a young Italian tenor who I'd never heard of named Luciano Pavarotti, was making his United States debut. So I said, "Hell, he's pretty good." And so that was a lot of fun going to my first San Francisco Opera experience, and due to UC Berkeley. The James Webb Space Telescope. This is an artist's drawing of it, and we'll talk a little bit more about that. It's also in JWST, and I'm going to talk to you first of all how it got its name. James Webb was not an astronomer, and most of the satellites and observatories and so forth have been named after famous astronomers, some of them who taught me. I'm old enough, so I actually have people who are now old enough to have satellites named after them. James Webb was the NASA administrator from 1961 to 1968. And he has an interesting history. He was basically a political appointee. He started as a administrative assistant to congressman in 1930s from his native North Carolina, moved all the way up and became, I believe, deputy treasury secretary in the 50s, and Kennedy named him as the NASA administrator in 1961. I think he was the second NASA administrator. It was a relatively new agency. And Kennedy met with him and with Lyndon Johnson in the early months of his administration and talked about doing a big project. And they decided, Kennedy said, is it possible that we might send a man to the moon? And Webb said, I think we can do it. And so in May of 1961, Kennedy said, we're going to do this ambitious project of sending a man to the moon. And James Webb took that over as his main task as administrator, running all the way through Lyndon Johnson's administration in 1968. And of course, the landing of the man on the moon was in 1969. So he was chosen as the namesake for the new telescope. This new generation telescope had been on the books for some time. I think the story is that in the mid-'80s, even before the Hubble telescope was launched into space, one of the astronomers was already thinking about something to follow up after the Hubble. And this became the next generation telescope, which then became the James Webb Telescope. In December 21st, from French Guiana, the telescope was launched, and you can see the launch right there. It was launched by the European Space Agency Ariane 5 rocket. Interestingly, no American rockets were available at that time. We had sort of, the rocket program for the United States had collapsed after the space shuttle. And in fact, we really don't have a major rocket program that's not non-commercial. The major vendor today is SpaceX, but SpaceX had not yet developed the rocket to the extent that they could launch a satellite as big as the James Webb Space Telescope. If you can look at this picture, can you look at the very top? That's where the top of the nose cone. Let me do this. The very top of the nose cone. And the interesting thing about that nose cone is that it's about 5 meters wide. And it turns out that telescope, the main mirror, is 6.3 meters wide. So you can see there's a problem there. And what was done, literally, was this telescope, there it is, 6.3 meters wide. Can you see my arrow at all? It's sort of floating around. I hope some people can see it. I'm moving it around. That's the diameter. And in fact, the base of the here, which we'll talk about more, is even larger than that. And so what was done was quite an engineering miracle. they folded the telescope up. So that's what the telescope looks like on the left, all folded up. And so it would fit inside the nose cone of the rocket. And this is on the right is just an artist drawing of a cutaway showing that. So this is an origami of gigantic proportions. And the problem is, as it goes into space, there's nobody out there helping it along to assemble the origami into its constituent shape. So that has to be all done mechanically. And it also has to have zero failures, because once you're out in space, there's no way to go out there and say, oh, let's give it a little nudge. So fortunately, it was done superbly. And you'll see in the next picture, this is how it went from the Earth. The Ariane 5 rocket took it out. The satellite was deployed, the telescope, and you can see the different parts of it came out. There was a solar array, communications, the sun shield, which is that big area that looks sort of like a football field, the secondary mirror, and if you look very carefully at the lower right, you can see it sort of sticking out to the right here. You see my arrow. That's where the secondary mirror is, and then the primary mirror is this big sort of golden shape, golden object. By the way, the telescope itself, the telescope mirror, is collapsed. And this is a design called segmented mirrors, which have been going along for quite a few years. In fact, one of the, Jerry Nelson, who was an astronomer engineer at Berkeley, was the first person to do these segmented mirrors. And so they're very common now with very large telescopes, but not folded up like that. You'll notice that on the bottom, it says L2. And it turns out there's a position in space, which I will talk a little bit about, named Lagrange point 2, or L2, which is where the telescope sits in space. And you can see it on the right-hand side. The Earth is there with the moon going around it, and to the left is sun. This is not to scale at all. But when Kepler first figured out the laws of planetary motion, and then Newton figured out that how gravity works, he developed the universal law of gravitation, and it could predict very well the actions of two bodies interacting with each other, like the sun and the Earth, or the Earth and the moon. But when you add a third body to the problem, for example, the moon, but in this case, the third body was the telescope, it turns out the solutions are not so easy. It's called a three-body problem, and it's not an easy problem to do mathematically. But there is a restricted form of that if the third body is very small compared to the other two bodies, and that's true of a telescope. The telescope's mass is much, much smaller. So Lagrange in the 1770s, which is a little bit after Newton, figured out the solution to this restricted three-body problem and found there were 5 positions in orbit with the Earth and the sun that would be stable in orbit. That is, they would move along essentially as a unified group. This is a little weird because if you think about it, if an object is further away from the sun than the Earth, it should be moving slower than the Earth, because as objects go further and further away, there's less gravity, and they would be pulled less by the sun and be moving slower in orbit. So for example, Jupiter is much farther away. It takes 12 years instead of 1 year to go around. But at L2, there's a very interesting thing happens. The Earth is in line with the sun, as you can see, And the Earth's mass acts like a little extra mass in the direction of the sun. And that creates a little extra pull on the satellite at L2, enough so that the satellite at L2 goes around the sun, in exactly 1 year, just like the Earth does. And so if you think about it, the sun is shining, the Earth is there, the Earth is blocking the sun, and at L2, most of the light of the sun is being blocked out by the Earth. And it continues that way as the Earth, satellite, and sun move around in a straight line as the Earth orbits the sun. So that's a very important point. L2 is a very important position, and other satellites have been launched into that position. It's 1 million miles away from the Earth, which is about 4 times farther than the moon. So it's quite a distant satellite rather than the typical satellites which orbit. The moon is about 240,000 miles away from the sun, away from the Earth. Typical satellites are tens of thousands of miles up, maybe 20,000 miles up, much closer to the Earth. This is really far from the Earth. Okay. I'm going to show you a ball. Can you all see the ball? This will demonstrate a little bit about how things work in space. If you look at the ball and pretend there's a marble in the middle of the ball, one of the things you'll find is that because of the shape of the ball, if you push the marble in any direction, a small amount, what happens to the marble? It rolls back toward the bottom of the ball. In any direction, the position at the very bottom of the ball is a stable position. It's called a local minimum. If you push the marble all the way outside the rim of the ball, then it'll fall out. But as long as it stays within that ball, it's a stable position. Well, L2 has this feature. It's partially stable, and I'll show you why. Next picture. Now, this is not a ball, but it has one characteristic of a ball. It's called a saddle shape, and this is the marble, the red dot in the middle. If you notice, if the red dot is pushed up the hill or up the other side, what will happen to it? It'll roll back down toward this position. However, if it's pushed toward you or away from you, what's going to happen? The marble's going to roll down and move out of that position. Well, the Lagrange point is this kind of saddle shape in terms of its gravitational pull. If it moves forward or backwards in its orbit, it comes back to its central position. But if it moves toward the Earth or away from the Earth, it will be unstable. So what happens, you don't want it to be right at the saddle point, because if it gets a little shove by various perturbations, it will move off and roll away from the Earth, which means it's away from the Lagrange point. So what the engineers do is place the satellite just almost to the top of the saddle, to this midpoint, and have a little rocket that's attached to the satellite, which pushes the telescope slightly ahead all the time, slightly away from the Earth, but so it stays in that same position, so it stays stable. That's very important because it takes a little bit of fuel for that to happen. All right, I hope that makes sense. You all took basic physics. Probably many of you didn't. So here's the two sides of the Webb telescope. The Webb telescope has a hot side. That's a side facing the Earth. It's far enough away from the Earth that the Earth does not block the entire energy of the sun. It looks like what is often called an annular eclipse. As viewed from the telescope, the sun is out there. The Earth is blocking most of the sun, but there will be a ring of energy around, which is the outside edge of the sun, still shining on the telescope. This is a hot side of the telescope. It has 185 degrees Fahrenheit or 85 degrees Celsius, so it's quite hot, not as hot as boiling water, but getting up there. And there's a lot of equipment on that side, including a solar panel, which is getting energy from the sun, creating electricity for the telescope. There's a communications antenna, which is sending all the information from the telescope back to the Earth. There's a computer, and there are this steering area, which has reaction wheels and jets. That's the little energy that's being pumped out to keep the satellite, to keep the telescope in the correct position. So it keeps it from rolling down that or moving toward the Earth. So it keeps it, and that's actually what limits the amount of time that the Webb telescope will have in space. Because when they shot up the rocket and had the telescope, they put in a certain amount of fuel. And what they did is they put in enough fuel to make sure that pretty much under almost any circumstance, they could have enough fuel to guide the Webb telescope into its proper position and have enough extra fuel to have it last between 5 and 10 years. And what happened is they did such a good job in conserving fuel to get it to the right position that there's more like 20 years worth of fuel. So it looks like the Webb telescope will be functional for at least 20 years, maybe even longer. So that's really good news. Well, let's look at the cold side. This is the side that's facing away from the sun, and there's a lot of insulation to keep all of this cold. Cold meaning really cold, minus 388 degrees Fahrenheit, colder than any place on the Earth, not quite down to absolute zero, but very, very cold. And here's where the science instruments are. This is the picture of the telescope mirrors and the detectors and so forth. They're all kept at this extremely low temperatures. Now, this will be very important as we talk about in a little bit. The temperature is kept cold with liquid helium, and helium is about as cold as you can get, and it's in there, and it's sealed inside the telescope so it doesn't evaporate. And so this is what is keeping all the detectors cold. And the shield here is blocking the light of the sun from coming to this side. So that keeps it very cold. Why very cold? Well, the major thing about the Webb telescope that makes it different from the Hubble telescope is that it's an infrared telescope. And infrared telescopes have some real advantages over visual telescopes, and we'll see some pictures to show you why that's true. But I want to have you do a little experiment about infrared energy. Infrared energy is not visible to the naked eye. And I'm going to have you pretend you are in a dark room. You're obviously not in a dark room, but you can take your hand, if you take your hand and move it very, very close to your cheek, but don't touch your cheek. Don't touch your cheek, just very, very close. Can you feel something? Can you feel the heat from your hand on your cheek without touching? This is a good test. You can ask if you want to get very close to somebody but not touch. You can tell when you're very close because you can feel their heat. the heat of their bodies. Any body that's above absolute zero emits some level of this infrared energy. We're at about 40 degrees Celsius, approximately 38 degrees Celsius, and we emit energy. Now, if you're in a dark room, you can look at your hand and you can't see anything because your hand does not radiate in the visible part of the spectrum, but it is radiating infrared energy. Well, that's very important because you can try this with a good friend also. This is a nice way to see how good a friend they are. The instruments, if there is a warm body or warm entity on the cold side, what's going to do is going to be radiating infrared energy and interfering with the ability of the telescope, because it will be flooding the telescope with essentially noise, infrared noise. And so that's why they have to keep the telescope extremely cold and keep it away from any infrared energy. Let me show you a picture of where we are compared to the, here's the Milky Way galaxy, and there are some labels here. I'm going to have you look very carefully. If you have a big screen, you can see it more easily, but below the middle, that's the center of the galaxy. We're in what's called a barred spiral galaxy. The center of the galaxy looks like a extended bar, and there are spiral arms that go off from the bar below and above and below, and there are a bunch of spiral arms. And you can see below, perhaps you can read this, the Perseus arm. Can you all see that? It's pretty easy to read. Above it is a smaller name called Orion spur, which is part of the arm, but it's a little spur from the arm. And above it is a very small word that says sun. So that's where we are. If you can see where my arrow is, I hope you can see that. And that's where we are. We're not in the middle of the galaxy. We're off to one side, and we're looking around in space. Now, the sun itself, it takes a few seconds for light to go across the face of the sun. So we say the sun is around 5 light seconds across. It takes about 5 seconds. It takes about 40 hours to 60 hours, depending on the exact dimension for the light to go across the solar system. Okay, so it takes a fair amount of time to get across the solar system. It takes about 100,000 years to get across the galaxy. So the galaxy is much larger than the solar system or the sun is. And the Earth, of course, is even smaller than that. Earth takes well, you can take 8,000 divided by 186,000. So it takes a 20th of a second or so to get across the Earth. Okay. That is a big galaxy, but not a huge galaxy. If you were going to a store, this would be an extra large galaxy, but not an XXL galaxy, and definitely not a large, medium, or small galaxy or extra small galaxy. I'm going to show you a picture of one of the Hubble telescope's great pictures, along with a James Webb telescope of the same region in space to get you started in this. The Hubble telescope, you can see, it's a telescope that observes in the visible part of the spectrum, what we see, naked eye. And this is an area of great star formation. There's lots of gas and dust, and you can see little stars here starting to form, and little globules here, which are also stars in formation. Now, the advantage of the infrared telescope, and this is one of the big advantages over the Hubble telescope, is that infrared energy passes through gas and dust really easily compared to visible light. So if you have gas and dust, you can see deeper into the cloud, which we are seeing, even through the cloud. Now, I want to point out a couple things to you. One is you can see these stars, which if you look carefully, these are the same stars as appear in the left-hand side, but you can see them much more clearly. The other thing is these spikes are not from the star itself. This is a diffraction pattern from the struts that are in the telescope. So if you ever see a star like this, it's not the way the star really looks. So the star really looks like a little tiny little dot or circle. Anytime you see these little spikes, that's from the telescope itself. Also, this is infrared. Remember, I told you can't see infrared energy. These are all false color pictures. These allow you to see the contrast in the different parts of the cloud, but this is not real color. These are fake colors. They've chosen different frequencies of infrared energy. They choose to make it a different color, but that's not the real color. These are real colors on the left-hand side. So you can see how much more detail you can see in the James Webb Telescope compared to the Hubble telescope. When we saw these views 30 years ago, 20 years ago, we said, oh my gosh, these are fantastic. Well, this is even more fantastic. So let's look at the electromagnetic spectrum to see what we're talking about. In the middle is what we see, from red in the middle here to violet. That's our range of the spectrum that we see. Higher energy, you get into ultraviolet, X-rays, and gamma rays. A little ultraviolet penetrates into our onto the Earth, and if you go onto the beach without putting on sunscreen, after a couple of hours, you'll know the effects of ultraviolet energy on your skin. Infrared is blocked in the Earth's atmosphere mostly by water vapor and carbon dioxide, which absorb infrared very well. And the fact that we're getting more and more infrared radiation captured by the carbon dioxide, which we're releasing, means the temperatures are going up. You know all about that. And then we have microwaves and then radio waves, which are longer, less energetic parts of the spectrum. And the infrared is where the James Webb Telescope works in the mid-infrared, and they also have a telescope in the near-infrared. Okay, sorry, next picture. Here are pictures from the two different cameras. This is the Tarantella Nebula. It's again an area of star formation. It's in the Milky Way, and you can see in the near-infrared camera, you can see stars behind here because these are again false color. These are both false color pictures. This is the spikes again from the diffraction grating of the diffraction struts of the secondary mirror, and you can see these, and you can see this detail of the dust and gas that are here. And on the right side, you can see a very different view. Looks similar, but the details are different because this is from the medium infrared, and because it's from the mid-infrared, the stars which are in this area, that's the same place as these stars are. These are just not as visible because those stars on the left are emitting visible light. They don't emit as much infrared light. Okay. So those are the two cameras. And I'm going to now show you some neat pictures. This is Jupiter taken by the Webb telescope. Again, false colors. You can see the red spot. You can see why they're false colors. This is doesn't look very red. These are the storms of belts of Jupiter, which are parts of the atmosphere of Jupiter. And look at the top and the bottom. Do you see this little red line up here? And then on the bottom, there's an almost identical red line. That's the auroras on Jupiter. So if you're there, it'd be like going, if you ever went on well, you probably wouldn't go on a cruise to Alaska at in the middle of winter, but particularly in winter, the areas near the north magnetic pole and also corresponding in the south magnetic pole, you get the aurora borealis and the aurora australis, and these are Jupiter's auroras. Here's another picture of a planet. This is Neptune. Neptune is down here in the middle. You can see Neptune has, this is the shape of Neptune. They also has clouds on Neptune. It also has rings. I don't know that you all know, but when I was going to college and high school and college, all we knew was that Saturn had rings. And of course, Saturn's rings are very prominent. Jupiter has rings. Neptune has rings, Uranus has rings. So all the four major planets in the solar system all have rings, and you can see the rings, and then you can see several of the satellites. There are 14 that we now know of going around Neptune, its moons. These are all minor gods and goddesses. I think these are mostly goddesses of the sea, because Neptune, of course, is the sea god. And then this big thing here is Triton. Triton's interesting. It's one of the largest moons in the solar system, and it's been known for a long time. And it's the only moon of Neptune that's going in the opposite direction in orbit. All the other moons are going basically from left. Here in this picture, it would be going this way. Triton goes the other direction. And so we're almost certain that Triton was a small planet going around the solar system, like Pluto, got too close to Neptune and got captured by it. So Triton is actually a captured planet, which has now become a moon. So it's sort of neat. And I'm trying to remember, I think it's bigger than our moon, which is one of the bigger moons in the solar system. I think Triton may be number 3 or number 4 in size in the solar system. Okay. Here's another picture of a planet, but this one is a spectrum. This is another instrument that the telescope has. It's called a single objects slitless spectroscope, slitless spectroscopy. And it shows the atmospheric composition of an exoplanet. It happens to be a hot gas giant exoplanet. We've discovered hundreds and hundreds of planets going around other star systems. A lot of that work was done at Berkeley, at Cal. It's one of the centers of exoplanet discovery. And you can see the spectrum of the atmosphere taken again in the near infrared. And as I told you before, water absorbs light, relies infrared energy. And here we can see the spectrum of water very clearly. These bumps are where the water molecules are absorbing infrared energy. And so this planet has water. And it's in the infrared. This is 0.75. This is expressed in microns. About 0.6 microns is about as far into the red as we can see. 0.6, 0.5, 0.4 is about what our visible part of the spectrum is. And then these are 0.7, 1.0, 1.25. These are into the infrared, but this is the near infrared, close to being visible, but not quite. All right. I'm going to show you another picture from the Webb telescope. This is again in the infrared. I have to emphasize that all these are false colors. This is a ring. This is a planetary nebula, which is caused by a star that has exploded. In this case, it's exploded many times, and it's a dying star called nova, supernova. They're usually novas. And what happens in this case is, again, I think this is the near infrared camera, and this is the regular infrared camera. if you look on the near infrared cameras, you can see this bright star. However, on this other one, you actually see it's two stars. And the one that's been exploding is the one on the left. It looks more red. And what's happened is this is a star at the end of its life. And stars which are over a certain mass will eject its mass every so often. It will eject its mass into space. And that's normally a nova, supernova. But in this case, it has a companion star. And it's close enough that the companion star, it's pulling, once it gets below this critical mass, it will stop throwing out gas. But then this star says, oh, here, you have some extra gas. And so it transfers some extra mass over to this other star. It builds up, so now it has a little bit more than the amount needed to explode, and explodes again. And so all these rings that you see are a succession of different explosions of gas that it's emitted over the years. And it will continue to do that until this star runs out of gas. So cool pictures. And by the way, this is a galaxy in the distance. You can see it very careful. On this side, you can see the nucleus of the center of the galaxy, and you can see the spiral arms of the galaxy out this way. It's viewed on its side. This is a nearby star, which has the spikes on it. Okay, this is the famous picture. This is the first picture they released from the Webb telescope. And it's a deep sky picture taken over, I think, a period of several days, accumulated the energy. And this is what would look like a blank part of space. But what it's done is to capture what's really out there. And aside from a few things that have spikes in them, like this one, this one, this one, almost everything here is a galaxy. Okay, so it's an amazing. You're looking at basically, in the middle is this giant galaxy, which turns out to be normally a giant elliptical galaxy, which could be 10 times the mass of the Milky Way. You can see on the right here, if you look carefully, you can see a little fuzziness around that. Those are rings. I mean, those are spiral arms, and that's a spiral galaxy. Oh, there are a bunch of spiral galaxies. There's one here, which has a little, it's a barred spiral with a ring spiral arm. There's another spiral galaxy up here. And then you'll see, so you see, there's just tons of galaxies there. You'll see these little swirly things, and I'll get to what those are, because that turns out to be, those are very important in this picture. So that's a deep sky image, and these get, as you go to fainter and fainter galaxies, they're fainter and fainter mostly because they're getting further and further away. They're further and further away from us. So I'm going to move into a little bit of history, which should be a little bit of fun. This is Edwin Hubble. The Hubble telescope was named after him. He was at the Palomar, and he worked mostly at Mount Wilson near Pasadena, where we have some of the people on the video today are from Pasadena. And he used the data of an interesting woman named Henrietta Leavitt. And I want to talk a little bit about her and about her colleagues. She lived from 1868 to 1923, so she died fairly young, in her early 50s. And she was a computer. She was hired by Harvard College, as they did a lot of women. And she worked on a particular kind of star called a Cepheid variable star. And she developed what's called the Levitt Law, which is, by the way, women in those days were not allowed to observe through the telescopes, but they could look at the data. And that's what she did. She looked at the data these photographic plates at the Harvard plate stacks, and I spent a lot of time there looking at these particular types of stars. They're very bright stars. The faintest of them are about 1,000 times as bright as the sun, and they go up to about 30,000 times as bright as the sun. And what she discovered was that they pulsate at a regular period from 3 days for shorter periods up to about 100 days. And what she found out that there was a very tight correlation between how long it took for them to pulsate and how bright they were. So that was a really important discovery, because it meant that if you could detect how long the star pulsates, you could tell how bright it was. And by seeing how bright it appeared in space compared to how bright it really was, you could tell the distance. And Mr. Hubble, Dr. Hubble, oh yeah, I want to tell a little bit more about this. So the Harvard hired a bunch of women to do this. They were all the computers. And this was taken in 1925, which is 2 years after Henrietta Leavitt died. There's a very famous one, Annie Cannon, who's right in the middle, sort of the senior person. And there are a whole bunch of other women here. And there's one really tall one, and I'll get back to her a little bit later. Cecilia Payne, her name was. And these women were often very highly educated without doctorates, but often had bachelor's degrees or master's degrees, and they were hired at low wages, of course, and did the computing at Harvard. There's Cecilia Payne. And Cecilia Payne, who later married Sergei Gaposchkin, was the first woman computer. She was hired from England to go to graduate school, and she got the first PhD ever issued by Harvard. And she later went on to become the first woman full professor at Harvard. And I was fortunate enough to get to know her and attended her first class, and actually worked around the corner from her for one summer, and I'll talk about it. Another woman who was her contemporary was Frances Wright, and Frances started as a secretary at the Harvard Observatory, and she ended up getting a PhD and ended up teaching at Harvard. And Frances in 1966 hired me during the summer to work on Cepheid variables. And she's quite a character. And here she is sitting at the observing chair of the Harvard 15-inch telescope, which in the mid 1800s was the biggest telescope in the world. It's now not nearly in that range. And Hubble used the data from these observations to develop the Hubble Law, which is the farther away a galaxy is from us, the faster it's moving away from us. So this is the famous Hubble Law, so that if you can measure the speed of the galaxy moving away from us, you can determine its distance. Now, it's not precise, but as you go out further, it has quite a good correlation. But that also means as you get further and further away, you're looking further and further back in time. And since this is a linear relationship, this is a little math, you can actually calculate how long did it take to get from where we are to where it is now. And it turns out along this line, it's all the same time. And that gives you approximately the age of the universe. So this is how at first we got to know the age of the universe. And here's the Hubble Law, the meaning. The greater the recessional velocity, the greater the distance. And we call it the redshift. It's actually a color shift toward the longer wavelength. So we can actually see by looking at the spectrum of the galaxy, we can measure the velocity, how fast it's going away from us. And for example, if you've ever heard an ambulance siren as it's coming toward you. Not only does it get louder, but with sound, its pitch gets higher. But then when it passes you, the pitch drops, and the change in the pitch is you can measure the speed of the ambulance. And the same thing you can do with a radar gun. So if you're ever stopped by a police person for speeding and they have a radar gun, that's what they use to measure your speed. It's essentially using what's called the Doppler shift, and that's the Hubble law comes from that. Okay, so that was a very big deal. I want to conclude with a couple pictures more. This is an interesting picture. This is a very compact cluster known as Stefans Quintet. Initially, there are 1, 2, and then 2 close together, 3, 4, 5 galaxies. And it's now called Stefans Quartet because this galaxy, the 4 galaxies, the top one, the middle 2, and the one down below, all have the same redshift, which we know from Hubble's law means they're all traveling, they're all at the same distance. This one has a much smaller redshift, it's actually much closer. And there was a big fight at Caltech because one professor thought this meant that Hubble's law was wrong because these have different redshifts. And the other person said, no, this galaxy is actually just closer. And they had offices they were in the same hallway. And they fought with each other for, I don't know, 25 years or so, arguing with each other. Halton Arp or Chip Arp and Alan Sandage. So it's a very interesting battle. Your opponent is a few feet from you. But Alan Sandage was proved correct. And then there's another one. This is a neat picture. This Cartwheel galaxy, again, some pretty pictures. There's some distant galaxies nearby. Here's one. Do you see that little spiral on the right? Much farther away, but it's in the same field. And then this one, which is my last picture. This is an Einstein ring. This was discovered, picture was taken in mid-September, so fairly recently. In the middle is a galaxy, quite a large, bright galaxy, except very far away. Around it is this ring. And what's the question? What is this ring? And I'll show you why. And it's called an Einstein ring for a reason. In 1912, Einstein came up with his general theory of relativity. And what he said was, if you have a galaxy or any object, and there's an object in between, it can actually bend the light that's emitted by the object and act like a lens, bending it. And here's we are at the Earth. So instead of the light going straight out, the light gets bent down back toward the Earth. So from the Earth, and why is it bent? It's because of the gravity of all these galaxies together. Particularly, usually there's a big giant galaxy which has a huge amount of mass causing this bending of light. So what do you see from the Earth? You see the galaxies here, and in particular, the one we just saw would be a giant galaxy and a ring of light around that galaxy. And the ring is coming from this one galaxy. So the ring is actually the light from one galaxy. And by measuring the redshift of this distant galaxy, we found with the James Webb Telescope, that particular ring is a galaxy that's about 12 billion light years from the Earth, almost 12 billion years old, which was about 90% or so to the beginning of the universe. So that's something that the Webb telescope will be doing a lot of, looking at these extremely distant objects. And they've so far discovered some very interesting things, like some of the galaxies are much larger and brighter than we expect at that distance. So this is, again, going back to that wonderful picture, all those little streaks here that seem to be centered around this galaxy, those are Einstein rings from some galaxy that's way behind this big galaxy. And what we're seeing is a light that's been bent by this large galaxy and some of the other galaxies around. And you can see little streaks all around here, which seem to be pretty much centered on this particular galaxy. And those are the Einstein rings going around there. Amazing picture. And with that, I will stop and see whether you have any questions. Okay, I don't know quite how to do this. I'm gonna, oh, okay, thank you.
Well, I will start, thus breaking the ice, Larry.
Okay, that's fine.
Let's talk about the false color renditions for a second. We know that, I believe that of the visible spectrum, red is the longest wavelength and violet is the shortest, right?
Right.
So did they apply the same kind of logic in doing the coloring, that in the infrared spectrum, the longest ones were assigned the color red, or is it some other?
I actually don't know. I know they what they try to do is create large contrast for the eye. So I'm actually not sure about that. That's a good question, but I don't know. I know they try to emphasize contrasting colors, so that may not have been exactly following that the formula. By the way, there's a nice way of remembering the colors. If some of you may know this, it's the name Roy G. Biv, ROY G initial BIV. So that's red, orange, yellow, green,
Blue.
blue, indigo, violet. Indigo is the one that's most people don't think about. Yeah. Anyway, yes. Go ahead. Any other questions people have?
Sarah has a question.
Sure.
Larry, I have been saying on mute, wow, 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 the whole way through. I really enjoyed your talk, and I had to raise the question of when did women finally officially get to look through the telescope?
That one I don't know, but I'll tell you this. I'll give you my little anecdote. When Frances Wright hired me for this summer job, she had me look at the plates that Henrietta Leavitt, the same kinds of plates that Henrietta Leavitt. I was looking at the Large Magellanic Cloud. If you look in the southern hemisphere, those of you who've traveled down to Australia and so forth, in the sky there are these two clouds that you can see, which are two nearby galaxies. And one's the Large Magellanic Cloud and the other one's a Small Magellanic Cloud. They were discovered by Magellan's crew. I don't know that he had made it that far. That he didn't travel around the world. His crew did, because he got stopped on the way. The advantage of those of looking at one galaxy is that basically all the stars are the same distance, or close enough to the same distance, so you can measure the Cepheid variables. So I measured the periods of Cepheid variables, and Sergei Gukopashkin, who was Cecilia's husband, was about 15 feet from me on the other side of the room, doing the same thing, except he had an assistant, so he was going much faster than I was. Cecilia, Mrs. G, we called her, was in the adjacent room with the door open, and so we could hear her pounding away on her Monroe calculator, doing the calculations of the periods. And for you to know about women at Harvard in those days, this was in the mid 60s, and she was a full professor and he was a research associate. So this was a little bit counter to what had often been the case in universities. They hire the man and bring on the wife as the research associate. They hired the woman and and hired the man as the research associate.
So how reliable are those charts? You're working off a chart, but the information originally came from viewing, right? Through the
Well,
telescope.
what happened is they took photographs, and the photographs were actually done on glass plates. So there were just rows and rows of glass plates room after room after room of glass plates. And so we would pull these quite large glass plates out and be looking at the original plates. And
Okay.
by having photographs that were taken over a period of weeks or months or years, you would have the data from stars changing in brightness. So you would compare their brightness to the surrounding stars, and then by having that data, then you could calculate the period of the Cepheid variable.
Thank you.
We have other questions. Raise your hand or speak up.
I will make one more comment. The other thing that I did when I was a senior, and another friend of mine who was a senior, we taught a woman named Sandy Morse, who's a first-year graduate student, how to use a telescope. And she ended up to be a university professor at UC Santa Cruz, and probably one of the most famous, Sandra Faber, and she's a super famous astronomer. So she became a lot better astronomer than I ever did.
Larry, the telescope, the unfolding didn't begin until the Lagrange point was reached, correct?
Well, they actually started doing certain parts as it was going out in orbit. So if you saw that slide, you could see they actually had points in which they were deploying these various things. So by the time it got there, it was already unfolded. It took 5 months for them to do all the testing and making sure everything was right before they started actually taking pictures, collimating, making sure that all the alignments were there.
So once it reached the L5, I think you called it.
L2
in
this case, yeah.
Once it reached that point, you talked about the ability to make small adjustments.
Right. What happens is,
why would they get out of adjustment in the first place?
What happens is it's actually the position of the telescope, because they cannot put it right at the L2 point. Because if you put it at the L2 point, if you remember the shape of the saddle, you were right at the top of the saddle. And if you think about riding a horse, if you're riding on a saddle, and if you slide forward or backward, the shape of the saddle keeps you in the middle. But if you slide off to one side or the other, and you don't have stirrups or something to hold you, you're on the ground, because the sideways is unstable. So what they do is actually, if you think about it this way, they, instead of mounting you right on the middle of the saddle, they mount you at the middle from the front to back, but they slide you slightly off to one side and then hold you there with, let's say, rope holding you from sort of the middle of the saddle to where you are, and that keeps you in place. Well, that's the same thing as what happens with the jets of gas. They put you slightly to the side and use these jets of gas to push you not quite to the middle, because they don't want you at the middle, because if you go the other way, you'll fall off on the other direction. So that's where the limitation on the lifetime of the Hubble of the Webb telescope is how much fuel they have to keep the telescope in the right position. So there are always constant small adjustments to keep it in just the right place.
Audrey, I think you have a question. You have to be off of mute.
Okay, there we go. Well, thank you very much for this very interesting talk. I'm thinking about your view with the Webb telescope of this galaxy that's almost 4 billion years old. And you're seeing it in the past or in the present?
Yeah,
And
yeah.
in the present.
The answer is you're actually seeing it in the past. If you think about it this way, if you look at the sun is actually 8 light minutes from the Earth. So if the sun were to turn off now, assuming it's a sunny day, turn it off now, we wouldn't know it for 8 minutes.
Okay.
So we're looking always into the past. And so in this case, for that ring, that Einstein ring that we saw near the end, that's about 12 billion light years from here. So this Einstein ring is from a galaxy that we're seeing it as it was 12 billion years ago. So it very well, it's going to look very different today.
Mhm.
If we go 12 billion years into the future and or get there immediately, we would see it look very different. The very bright stars will have already burnt out, and it'll probably be quite reddish in color, as only the cooler stars will be remaining. Yeah.
So now that we can see what it looked like 3.9 billion years ago,
Yeah.
what does that allow us to do, or what does it what information does that give us about the formation of the universe? Or
Yes, what we're doing is seeing snapshots. A way of looking at that is if you could take, okay, there's a way of looking, let's say you're looking at pictures of your children, and you're looking at one child, and you're seeing a picture of the child from his or her birth to now they're 40 years old, and you can see the development of the child. Well, we don't have that advantage in astronomy because we can't see that long. We can't wait that long a period of time because stars last, we're talking about at least hundreds of millions of years or billions of years. So what we're doing is looking at a whole population of children. Some of them are 40 years old, some of them are 35, some of them, and the further back you go, the closer you can see to how they were when they were born. And so if you're looking back, if you're looking at a child who's just been born, just out of the womb, you're getting very close to that sort of moment of birth that you might not be able to photograph, or certainly the child inside the womb, almost about to come out, you can't see that. And so what we do, the closer we get to that early time, the closer we're seeing what the universe was like at that point. And by seeing all these different pictures from different distances, we're also seeing further and further back in time. So when you add that all together, you're getting essentially a picture of the evolution of the universe. But the analogy would be by looking at different children of different ages all the way to adults, you can piece together what it would what it would look like, even though you can't see any individual moving through time for that length of time. I hope that.
can we think that we can foresee what our Earth is going to look like in?
Yeah, we have a pretty good idea what the sun is going to be like in 5 billion years. We think the sun will last about 10 billion years. We've been around for 5 billion years. The Earth itself, yeah, we have pretty good models. The models of stellar structure and stellar evolution, which is what I worked on, are quite good. And I think we'll know that probably our sun will die out. It will probably expand to maybe the orbit of Mercury or Venus. Will be the Earth will be toasted. Nobody will be around by that point, but the Earth itself won't. Well, it probably will be there, but it won't be in any condition for any life. And then the sun will become a white dwarf, will become a much fainter star, and not enough radiation when it runs out of fuel. Other stars blow up, and the planets that might be around them aren't around.
Mhm.
Yeah.
Okay, thank you.
You're welcome. Mark had a question?
Yeah, I have a question about these spiky diffraction patterns, I guess. Do they cause any functional limitations to the telescope? It seems like if you look closely enough, just about every star or every point has these spikes.
Right. Anything that goes through a telescope that has struts like that will cause diffraction patterns. Yeah, there's normally we aren't looking at the shapes that much. More looking at the spectrum, the colors. So that doesn't affect us too much. But there are some problems with that if you're trying to see whether there are problems with shape stars that are not perfectly circular. There are perfectly spherical. There are some pictures that there are some stars that have elongations and so forth that tends to make more difficult. If you can get them close enough with powerful enough telescopes, you can actually resolve the disk of the star, and therefore you can actually that makes it easier to see. Like, you don't have any problems with more extended objects like planets. You don't get the diffraction because it cancels out basically, or it gets blurred. So anything that's larger that you don't have so much trouble. But when you're talking about a point source, that's where the diffraction is the problem.
Great, thanks.
You're welcome. Anything else? Anyone else have a hand raised or anything else? I can't answer about everything, but astronomy is one of the things that I gave another talk a few months ago, and one of the problems is that when I graduated from college and graduate school, we thought we knew pretty much most of everything. You know, everything wasn't decided, but we thought we knew most of everything. And then the problem dark matter came up, and then more recently dark energy. And so right now, I think we know pretty much about everything about 5, 6, 7% of the universe, and 93 to 95% of the universe. We have really no idea what it's like. So it's an interesting time to be an astronomer because there's so much that we don't know. But you can't be complacent in these science fields. And astronomy has probably changed more than anything else. It doesn't affect how we live our lives mostly, but it's, you know, when you think you know everything and then you think, well, maybe we're at 5%, well, it's a big change.
Mark, I'd like to ask you about the Milky Way galaxy. Early on, you showed a picture of it as if viewed from the top above it.
Yeah.
Of course, that's some kind of an artist rendering. We've never sent an instrument.
Absolutely. Yeah.
So how do we know the shape of our galaxy then? If we
yeah, we can see other galaxies from different angles, and so we can say from our position we see similar things, and so you can extrapolate. But you also can measure distances to the spiral arms are pretty well delineated, even if you see them on edge, because if you can tell the distances to the objects, the brightness of the particular regions of the spiral arms where there's star formation, and they tend to be very bright, so that's fairly easy to see. And also the center of the galaxy, we can. It's a little tricky. You see it mostly in the infrared, but you can see toward the constellation. If you know the constellation of Sagittarius is the direction of the center of the galaxy, and you can actually see the shape. In fact, that's how we learned it was a barred spiral rather than we thought when I was growing up, we always thought it was a regular spiral, but the more detailed observations show that it's a bar. The nucleus of the galaxy extends rather than being spherical.
Did I see a hand raised?
Oh, where's my background picture? This is Lake Lafayette. No, it's not. It's does anyone know where this is? Somebody should know. This is Emerald Bay in Lake Tahoe. So it's not Orinda. Okay.
Okay.
Where I live. Okay. Anyone else?
Mark has a follow-up.
Yes, one further question. Has there been any thought or designs incorporated into the telescope that would make a service mission possible in the distant future when it runs out of fuel or when something needs to be attended to?
Yeah, this is the problem with the Webb telescope. It's 4 times further away than the moon. So it's much farther than any kind of service mission we could do. The Hubble telescope is, relatively speaking, next door. So you can send up, we sent up missions to fix the Hubble, but the Webb telescope is, it's just too far away. So the answer is probably no. It's not. It's certainly not within the lifetime. I think we won't be able to send people out that far in our lifetime. That's 4 times farther than the moon.
I think Elon Musk may have something to say about that.
He might. There might be something there. You can send a Tesla van out there to fix it. Yeah, it's an interesting thing because there are satellites that have been sent out much farther than the Earth-Moon distance out into the solar system. Of course, the Voyager program, which started in the 70s, is now the first Voyager, I think, is out beyond the orbit of Pluto. So it's gone out basically past all the major planets and is sort of heading toward the stars. It's still, remember, I said that we're talking about maybe a few light days if you think about, and then we're talking about the closest star are light years away. So it's, if you think about taking a walk, you can sort of do a hike over a couple of days if you're a real adventurous. Taking a hike over 4 years, that's sort of the comparison. It's a much greater challenge. If you want to have a sort of a sneak into that, take a look at the first Star Trek movie, and the sort of the hero villain is this thing called V'ger, which is supposedly a corruption of what happened when the Voyager spacecraft went out so far away and it got found by aliens and it was transmuted into this villain, which is part of the story of the Star Trek 1 movie. Okay, anybody else? Any other questions that you have? Anyway.
Well, given that, Larry, we really want to thank you for today
Oh, absolutely.
and all of your time. Bravo.
Okay, well, thank you. It was
Thank you.
fun to do, and looking forward to having more collaborations with Lamorinda Village. We aren't as well, we don't plan as far in advance as you do. You guys are really great about that, and so we very much enjoy you sharing. You have one of our members, another one of our members talking in February, I think. John Schwartzberg, who's one of our members, is going to give you a talk also on COVID. He's an expert on COVID, so, and all infectious diseases and so forth. So that'll be fun.
Yeah, this is at least his second presentation to us on COVID.
Yeah. He was a professor at School of Public Health at Berkeley for many years.
Right.
And so he's great. Well, thank you all.
Thank you.
Fun. It was fun.
Thank you.
Take care.
And Larry, join us some other time for
Okay.
future presentations.
Yeah. Great. Thank you.
Spectator.
Take care.
Thank you.
Thank
Bye.
you.
Bye-bye.
Thank you, Larry.
You're welcome.
Bye.